Welcome. So we said it's energy. So the first thing you notice is that it is actually a form of energy. Yeah. And then they said a form of energy in joule, measured in joules. That's the unit. And don't mistake it for temperature. It is actually a form of energy. You can see it's a form of energy. Why temperature is just like degree of hotness or coldness. So don't mix them up. And also they said particles move about and take up more room if heated. Yeah, that has to do with kinetic molecular theory. We'll still talk about that later. So, yeah, this is just to introduce you to what it is as a form of energy. So, we said temperature is the degree of hotness or coldness, right? So, to measure temperature, what do we use? We use what? A thermometer. And then for a thermometer to work, we need what we call the thermometric properties. So basically, the thermometric property is just what changes with temperature. For example, there is a thermometer called optical form of thermometer that are called optical pyrometer. So the way it works is that it uses light intensity. So as the temperature is increasing, the intensity or the radiance energy of that part this thing will be getting more. So that's what we call the thermometric. For those, so they said physical properties that can change measurably. So let's as some that thing changes, just like, oh, this thing has changed, then that means that the temperature is this high. So basically that's what thermometric properties are. So yeah, they said length of column liquid. Yeah. So as the liquid expands, does the temperature uh increases length of this thing. So this is actually talking about the liquid in glass thermometer, which basically means that it uses water microprop. It uses the expansion of liquid. So let's say we have a liquid inside a glass or something like that. As much as the liquid expand, that means that, oh, the temperature has increased. So we just measure it and compare it. That's basically what thermometric property means. Physical properties that actually changes. So the first one we talk about is the constant volume gas thermometer. So the thermal property here is pressure. It actually has to do with the expansion of gas, and this is actually the most accurate form of. You don't really need that, sha, but just know that this is actually like the most accurate form of thermometer. So you have the constant pressure gas thermometer. The thermal property is the volume of gas, and then we have the electrical resistance thermometer. So this one uses what? Uses the resistance of a metal. That's the thermocouple. And then thermocouple, please note this, all these thermometric properties. Mercury in glass, like I said, length, this is actually volume 2, like how the liquid expands. So basically most of the thermometers you are going to find in your maybe your laboratory and stuff like that are actually liquid in gas thermometer, which basically could be water or alcohol or mercury. Yeah. So yeah, we look at important thermometer terms. So yeah, we talk about the upper fixed point. This is what they mean by upper fixed point. Like for let's say the Celsius scale. So the temperature at which pure water. Please notice pure water, because once the water is not pure, the boiling point will definitely be affected. And they said the lower fixed point, which is 0.4 Celsius, at which pure ice melt. So there's, like I said, liquid used inside thermometer, and the scales are basically like the units we use. So we have different scale, but the one that you should be concerned with for now is basically the Celsius, Kelvin, Fahrenheit. Yeah, I think we have still have rumor, Rankine scale or stuff like that. Yeah, you don't really need all those for this exam. So basically just know what the upper fixed. They can even ask in your exam like, what does upper fixed point mean? Just basically know what it means. The lower fixed point to temperature at which pure ice melt, and the value for it in social. So I said we can talk about the thermometric substance for liquid in gas. So they can ask, yeah, it's a common question like, why is mercury preferred to alcohol? The first they said is has a high boiling point. That means that should tell you that this one, the boiling point is 78 degrees Celsius. That means that something above 78, greater than 78, we cannot use this guy alcohol thermometer to measure it. Do you get what I'm trying to say? Yeah, it should be clear. So higher melting point, yeah, is a good thermal conductor. This one conduct more, expand regularly. So this actually undergoes irregular expansion which make it harder to even read the thermometer. This does not wet glass, this wet glass. So note all these features why mercury is actually preferred as the thermometric liquid compared to alcohol. So another thing, important thing you should know is what we call the absolute zero. So basically, they said the odor positive temperature is called absolute zero. This is measured in Kelvin scale. You know, I told you we have Celsius, Fahrenheit, and the Kelvin scale. So basically, it's the lowest temperature. You know, one thing you should know is that every form of matter actually has molecules. So as the temperature is increasing, that means the molecules are gaining kinetic energy. Let's say we have something like this. Let's say we have gases. So as you increase the temperature, then basically the kinetic energy will definitely be increasing. So this absolute zero is something you should know, very very important. So they said this is the point all atomic and molecular motion stop. That means that this is the lowest possible. You know, another thing you notice that on the Kelvin scale there is no negative. It's the lowest is zero. That means that absolute zero is what, 0 Kelvin. That's the lowest form of temperature you can actually achieve on the Kelvin scale. So to convert, this is the formula. You all should know this. To convert Kelvin to Celsius, just 273 plus. So they said Kelvin is used without a degree. Yeah, it's just your K. I'm not sure they should test that in your exam, basically. So let's continue. So this is basically testing our upper fixed point and lower fixed point. So this is Celsius. This is the upper point is 100 degrees Celsius, abi 0 degrees Celsius for the lower fixed point. And I already said lower fixed point is the point at which pure pure ice melts, abi now. So basically this they can actually ask us to convert from one scale to another. You see, we have Celsius, Fahrenheit, and Kelvin. So for example, we can have to do this. It's very very simple. This is the temperature we are looking for. So if they give you a temperature in Fahrenheit, you are just going to take it to the other scale. So for example, this one will be what, let's say you want to convert from uh Celsius to Fahrenheit. You can see the lower fixed point Fahrenheit is 32 degrees Fahrenheit. And don't forget that Kelvin does not have a degree. So that would be x minus what, 0 over this minus this over this minus this. Have been 100 minus 0 0. You see, you can have something like that for this one too. Let's do it for Fahrenheit here. That would be y minus 32. Abi, sorry, this thing is not writing very well. Over 212 minus 32. So we just compared both. So you can be wondering that what is this guy doing? What is this? So let's see how questions can come. It can come in different form. Let's just see. So this is the continuation of what I did there. Look at this carefully. Can you see it? Look at this carefully. So, oh sorry. Look at this. So look at this. 100, 0, 212, 32. This is Fahrenheit. I'll be Fahrenheit scale. So we are the temperature we are going to ask you to convert to from here will just be the C or F. So just C minus 0. This one minus this one. Very very easy. This one minus this one. 100 minus 0. F minus 32. This one minus this one. So that's C over 100 multiplied by F over 32. So that's where we have our popular formula. So if you are a smart student, you basically know that you anytime you are given to calculate from this one, this is the formula you're just supposed to use happy now. So but then you can just know it like that, sha. So the most important thing to know is that if you have to scale this one minus this one, so they can frame the question anyhow. Let me just look at one beautiful one from your exam. So look at this question. They said a well-lagged bar of 100 centimeter has its end maintained as 100. That means the end of the this is the metal bar where I'm still using this is the metal bar. This is the end maintained at what, 100 degrees Celsius abi now. So and 40 respectively. That means the ends, the upper one and the lower one, this one is 40. That's the lower end. Please listen to me carefully. It's very very easy. Towards the temperature at a point 60 centimeter outer 50 centimeter from the outer end. So basically they said 100 centimeter. So here now look at what they did. They are not even using the length in form of another scale. They are using it in form of blend. They are just testing if you actually know the conversion. So here we have what? Sorry. Here we have 100, and here we have what? We have what's it called? We have 0 centimeter. Why is there 0 centimeter? This is a rod 100 centimeter long. If you measure it, if it is 100, the upper end like this 100 centimeter, what will here be? That's what I did here, upper, and this one is the temperature. So you are comparing the temperatures. It now said what is the temperature at the point 60 centimeter from the outer end. So that means that they are asking that if what at this point from the outer end, let's say this is the outer end here at the end abi that 100 degrees Celsius. So 60 centimeter from it, that will be the point of 40 centimeter. Why is it 40? But they say 60 now. Let's listen to me carefully. They say 60 centimeter from the outer end. That means that the difference between that point we are talking about and 100 centimeter is 60. That's 40. Do you guys get what I'm trying to say? So basically, what we are going to have is something like this. So what we are going to have is something like this. This will be our end image. This is 100. Sorry, the writing is not fun. Just follow. I will still send, I might send a picture. Sure. This is 40. This is 0. I already explained how we got 40 because they said 60 centimeter from the outer end. That means the difference between them is 60. Don't use 60 here, please. So this is 100 degrees. 100 degrees Celsius, and this is C. Because this is what you are looking for there. So they're asking that at this 40 centimeter, what is the temperature? You see that they're on the same line, and then this is what 40 degrees Celsius. So I didn't mean they said this is another thermometer. They said they can just give you the upper and lower freeze point of a particular thermometer. They say if the thermometer has like 200 as upper freeze point, that will be here. 50 as the lower freeze point, and then at the temperature that corresponds, what's the temperature on Celsius? They can say on Kelvin something. Just that's why you have to know the upper and lower freeze point for each of them, so they can say what temperature on it corresponds to this on this. So basically, what we are going to have is what this minus this, and this minus this minus this minus this, then you equate it. That will be C minus 40 over 60. Why did I get the 60? 100 minus 40. B is equals to 40 over 100. Why did you get the 100? This minus this minus, just the same way we did this. So we are just basically going to equate them. Let me take it to a new page. So we have C minus 40 over 60 equals to 40 over 100. When you cross multiply, you're going to have 2400 over 100 is equals to C minus 40. Abi now, I just put this one in brackets. So when this one multiplied with this one getting 2400, then divided by this one, then equate it to this one. Abi now, that's 24. Abi now, sorry, let me take it to a new page. So we have 24 equals to C minus 40. That will be what? C minus 40 is equals to what? 64 degrees Celsius. That's all. So basically, you see what I did. So you can just look for more examples on how it works for what's it called? It works for different skills. So I used something that could be more technical. What they will most likely give you is just they might not give you this centimeter of a length of a bar of iron. Sorry. So but they might just give you another skill. So you just have to know where to put my upper freeze point, lower freeze point, then equate it. This one minus this one over this one minus this one, and this one minus this one, this one minus this one. So what you are looking for is most likely in the middle, and what you are being given is here. So basically that's all. So this is for the first part on it. So this is the second part for it. So what we have here is, what is heat capacity? So heat capacity is the amount of heat required to raise the temperature of a body. So the amount of heat, the total amount of heat to raise the body temperature of a body by 1 degree Celsius or Kelvin. Please take note, this can come out in your OBJ exam. Yeah, so the formula is C equals to what? Q per change in theta. Abi? Yeah, so this is basically, so the Q here is our heat energy. So you can see the formula Q, and please note that what we talk about when we get to specific heat capacity. So this one has to do with of a body, that it has to do with the whole body, the whole body. So the C there stands for heat capacity, joules per Kelvin. Yeah, and Q is heat energy, change in temperature. So I think I've seen this in past question before. That its capacity depends on what? So it depends on the nature and the mass of the object. You can see that it depends on the nature and the mass of the object. So that means that different objects we have what? Different heat capacity. That means that the amount of heat required to raise different body by 1 Kelvin or degree Celsius will differ based on the nature of the materials. So let's move to specific heat capacity. You can see that that one is heat capacity, this one is specific. So the key difference is actually that temperature of 1 kilogram of a substance, 1 kilogram. That's why it's called specific. It's specific, unless that one has just already its capacity, that's just the total body. So this one is 1 kilogram of. So the key difference between them is that the unit. Look at the unit. The unit here is joules per kilogram per Kelvin or per Celsius. So it's just joules per Kelvin. So you can see that this one includes mass. Yeah, mass is very, very important in this one. So let's continue. So let's move into the heat formula. So we said we already gave the formula for this one, C. That is specific capacity to be what? Q over what? MC. Sorry. So Q over MC theta, then MC. So Q is equals to MC change theta. So they've given you that it supplies in joules. So if they give you a body, like they can just say in your question like something increases by this, calculate the amount of heat. Just look for your mass, your specific heat capacity of the particular substance, and then your change in temperature. Change temperature is basically like, okay, we increase it from 30 to 50 to 50. What change? That's 50 minus 30. Abi that's final minus initial temperature. So another thing that is important is calorimetry. Calorimetry is basically mixing of this thing. Although I think you just need to get the basic knowledge. You don't need to go very deep for now. So basically, what calorimetry says is that heat loss equals to heat gain. What does that mean? Let's say you want to bath now. You have a temperature of theta 1, which is 30 degrees Celsius, Abi. Then you have hot water of 70 or theta 2, that's 70 degrees Celsius. 70 degrees Celsius. So basically, you mix them together. What they're just trying to say is that the heat lost by this guy is equals to heat gain by this guy. That's it. Yeah. This is heat is considered as Q1. So this negative is just implying what it that this guy is losing it. What does it mean to lose it? When you mix cold water and hot water, basically the hot water will basically lose it to the cold water. So the heat it lost, where did it go? It was gained by the cold water, definitely. So basically what they are trying to say is that it's lost by the, so like we explained the other time, it's also part of law of what? Conservation of energy. That is, you are just transferring energy. Energy is not really being lost. So another important aspect you should be familiar with is electrical appliances. So basically, don't forget uh, power P is cost to what? Energy over time. Abi now. So basically, power times time can give you energy. So this energy could be what? Q. That is heat energy. Does that make sense? Basically, they can just tell you that calculate the amount of this thing. So you can see energy is equals to power times time is already written here. So basically you can just use it in electric power. So the only job you have to do here is to find the formulas for electric power. So they use heat to represent energy is equals to what? Power times time. That will be IVT, and it could be what? I square RT. I square R is a formula for power in electricity multiplied by time, abi. So basically that will give you what? H. So they can just give you an electrical appliance and say that, oh, this particular so electrical appliance was heated through blah blah blah, calculate the power, or they can just give you. So it can come in any form. So let's look at some questions. So you can see all these things are very easy. So let's look at some questions. So the first question we have here is that 200 gram of water at 90 is mixed with 100 gram of water at 30. What is the final temperature? So basically, this is actually a very simple question, but something like this should come. It's like a very popular question in JAMB. So this something like this could come in exam. So what we are doing here is calorimetry. Abi now. So who is the person losing it? 200 gram of 90 degrees Celsius. Abi now. Who is the guy gaining it? This 100 gram. So what are we going to do? Minus Q equals to Q. Abi now, that means that the heat lost by this guy equals to heat gained by this guy. And then when you are mixing them, there will be a final equilibrium temperature. What does equilibrium mean? When you mix this 90 plus 30, the temperature given you will definitely be lesser than 90. Abi now, because this one should be colder. So that equilibrium temperature, we are going to represent this with T. So and that will be higher than 30, Abi, but lower than 90. That should make sense, right? So what you are going to have is what? Q1 equals to what? Q2. Q2. Abi now. That's M1 C1 theta 1 minus T. That's heat loss. You can be wondering, what is theta 1 minus T? Basically, I already told you that we had it at 90 degrees Celsius. Abi now. So 90 degrees Celsius, that's our first temperature. Minus T. Why is it minus T? Basically, it's losing heat. And the temperature that will be formed, that is warm temperature, because when you mix cold things and hot things, you're going to get warm, should be lesser than this, should be lesser than the 90 we have. So that was theta 1 minus T is equals to M2 C2 T minus theta 2. But this one is theta 1 minus 8. Why is this one T minus theta 2? Basically, I already told you that the equilibrium temperature should be higher than this one. So this is heat gained. You know, remember we already talked that Q is equals to MC change in theta, Abi. So I'm just bringing out the change in theta part. What I think you guys should be following. So M1 is one in theta, just know where to put it. And you will agree with me that what we have here is basically water. So that should, I already told you that the specific heat capacity, it varies from substance to substance. So no matter how you want to solve this guy should cancel out this guy. Does that make sense? Why? Water has specific capacity. Abi, it's constant. So basically, it's like around 4,200 joules per kilogram per Kelvin. So basically, it's definitely going to cancel out. To make things easier for ourselves, so we are left with M1. So let's just basically we are left with 290 minus T equals to what? Equals to 100 into bracket T minus 30. So basically 2 minus 30. So we are going to solve for T. Abina, because they said what is the final temperature of the mixture. So basically we are going to solve for T. So just how will I put it? Just use these guys to open the bracket, or let's just make things easier for ourselves. This should cancel this, so we're left with 2 Abby. That would be 290 minus T equals to T minus 30 Abby now. So basically that will, let's just what we're going to do is use this one to open the bracket, then we collect the like terms. So we'll be having something like 180 minus 2t equals to 30 minus 30. So when we carry this 30 to the other side, we'll be having 210 equals to 30t. T is equals to 70 degrees Celsius. So basically this can come in any form. So you can see how we actually solved this thing. I can go with me now that I said the temperature we are going to run will be greater than 30, greater than 30 degrees Celsius. Now, so basically what that shows is that and this question can come in any form. They might not even give you any. They can just say that the mass is twice something. Just don't be confused. So apart from the way we had it here, we can have it another round. Let's say the power in terms of electricity. You can see they said an immersion it 400 watts. That is the power. We've done work energy and power. So 220 volts 220 volts used to hit a liquid of mass, something of mass 0.5 kilogram. It's increased uniformly at the rate of, so this rate of increasing the temperature means that what, change in theta per seconds. That means it per second. Now let me just use t. That means that they have given us two things here: the change in theta and the second. Change theta is what, 2.5 degrees Celsius. That's the change, and the time is what, 1 seconds. Where did I get this from? They already told you per seconds, per 1 seconds. So don't confuse it, don't mix things up. So our power is what? Power is 400 watts. Yes. Mass is what? 0.5 kilogram. Abi, then this thing, the volts, which V is equals to 200, V is equals to 200, and then we have the time to be 1 second. Time is 1 second, and change in theta is 2.5 degrees Celsius. So this is basically all the parameters that we have. These are the parameters. So the formula is what? Power times time is equals to mc change in theta. What's this formula? I already explained it. So basically, if you take this one, that will be power is equals to energy over time. That basically explain our this thing. What's it called? That basically explain our formula for power. So we have, what are we looking for? We are looking for the specific heat capacity, Abi. See, so we have 400 times 1 equals to 0.5 times C times 2.5. So basically we'll be having C equals to 400 over 0.5 times 2.5 equals to what? Equals to, sorry about my handwriting. I don't really have a very fine handwriting. Just try and follow. So that would give you what? 320 joules per kilogram per Kelvin. So basically that's specific capacity. So it's very easy and very easy to approach. So what is latent heat? So basically this latent heat, so this is when a solid melts or liquid boils, energy must be added and the temperature must remain constant. The amount of energy it takes to melt or boil certain amount of material is called latent heat. So this is just basic English. What does latent heat mean? Latent means something hidden. So so latent means hidden. That's hidden heat. So basically what you're trying to say here is that when you want to change something from one state to another, I'm talking about state of matter. So basically let's say you want to change from solid to liquid. Let's say ice, you want to melt ice. So they said um the way it works is that you are going to be increasing the temperature of the rice gradually until you get to the point of change in temperature or change in state. That particular point when you want to change the state, the temperature does not increase. That means that you wonder how come we are adding more heat and the temperature is not increasing. The temperature you are the heat you are supplying is being used to break down the forces, the molecules, the intermolecular forces of that particular ice is not using to increase the temperature again. Do you get that? So basically that means that every change in state occurs at a constant temperature. So basically you will still get it. So basically just like it is to boil certain method of boil at a constant temperature. So just note that. Let's move to the next page. So basically this is very beautiful. You can see this graph here. See melting. You can see that melting, let's say we add ice at minus 40 degrees Celsius abi now. So this is ice minus 40. From minus 40 we took it to what? Ice. It's still ice. So ice here is minus 40 degrees Celsius. Please listen to me carefully. So minus 40 degrees Celsius, look at what we have here. We have ice at what? 0 degrees Celsius. This is solid, this is still solid. The temperature has changed, right? So before the other stage you are going to have here is what? Water at 0. So at this particular point where ice is being changed, this point where ice is being changed to water, the amount of heat being supplied there is called what? The latent heat. Latent means hidden. I already said that. So this heat, you will not see it because the temperature will not increase. But then this is the particular heat that is required to break down this ice, the intermolecular force of this ice towards to water. You get that. You can see that it occurs at this constant temperature. You can look at this too. Water boiling. See that boiling occurs at 100 degrees Celsius and we'll be increasing the temperature from liquid before it turns to gas. You already see that it's constant here. It's constant. Do you get what that means? So basically that latent heat is shows that its change of matter occurs at a constant temperature. So we can see latent heat is the amount of change state without changing its temperature. I've already said this. So we can have different type of latent heat. So latent heat is of fusion. So it needs to change solid to liquid at melting point. That means that 1 kilogram. So that's for ice at 0. I already said that too. Water at 0. You see that the temperature is still on that, but then the state has changed. So basically it occurs at this constant temperature, and the formula is what? Q is equals to ml. So which one is the latent of vaporization? What does vaporization mean? Liquid to gas. See that Q is equals to mlv. So basically you already know we talk about Q is equals to mc change theta. So here there is no change in theta. Why? Because it's latent heat. So it's just ml. equals Q equals to what? ml, that is mass times latent heat. So in any question they can just tell you that we change this, calculate the latent heat. This one is even easier than it specific heat capacity. So you see, that's basically what latent heat means. So look at this beautiful question. They said the amount 200 grams of ice is turned to water at zero, at minus 10 degrees Celsius, rather 200 grams of. So find the heat required. Basically, if you are going to ask something in your exam relating to this, they are definitely going to ask something like this. So they said ice at minus 10. Follow me. So sorry, they said ice at minus 10, right? So to water at zero. So we have ice at minus 10 degrees Celsius. That's solid, abi? Ice. So the amount of heat required to what? To ice at zero. You see that it's still ice. So the amount of heat here required here plus the amount of heat required here. This is water at 0 degrees Celsius. Yeah, is what you see that here now. The heat that is occurring here is not latent heat. The Q1 here is not latent heat, abi. So this one is latent heat. But why? How do you know this one is latent? This one is not latent heat. Latent means hidden. Do you see any change in temperature here? This is ice at 0. This is water at 0. Are they not at the same temperature? Yes, they are. So basically, what is happening is that you just have to know that it's happening at the same temperature. So the total heat required, Q is equals to Q1 plus what? Q2. So what's Q1? Q1 is the heat here. Q1 plus Q2, that's the total heat you used to change ice from minus 10 degrees Celsius to water at 0 degrees Celsius. So what is the difference? This one, it will be, this Q will be equals to what? ml, abi now. So this one will now be latent heat of what? Of fusion. They are definitely going to give you in your what's it called, in your question. So and then here will be what? Q is equals to mc changing theta. Why is it changing theta? We already see that temperature is changing. So you are not going to use the formula for this one. You're going to use the formula. They now said you are taking this water to another temperature now. That's how it's going to continue. You just have to understand how it works. So basically, so you are going to calculate this Q is equal to mc theta. Take it, bring it here. Calculate Q is equal to ml. Then bring it here. Then you add both together. That's the total heat required. That should be clear. So let's look at how it's solved. So I already told you that they will give you the specific capacity of ice and water. Please don't mix the capacity of ice with water. They are not the same thing. So you see that this one is 2.1 joules per gram per Celsius. So this one is just joules per gram. That's latent heat. You see that latent heat of fusion. So they said, I already told you the first one, Q1 is what? Q is equals to MC change theta. That's M. What's M? 200 gamma 5. C. What's C? Change theta is what? 10 to 0. 10 minus 0. Happy now. That's 4,200 joules. Does that make sense? So the second one is to melt ice. That's, I already told you that Q2. Like from here, I already told you that Q2 is what? ML. So basically, that's what we did here. M, that's 200 times L, intensity of fusion. They've already given us, they will give you the capacity and this thing in your, or what's it called, in your question. So you add both together, you get 71,000 joules. That should make a lot of sense now. So I think we are done with this question. So if you see any, I didn't mean they said we are still taking that particular water, this water 0 to steam or vapor at 100 degrees Celsius. How do we go about that? When we've gotten to water at 0, that means that we take it to what? Water at 100, abi? Before taking it from 100 to steam at 100. So this one will be latent heat of vaporization, and this one will still be MC change theta. So the steam we are going to use here is specific capacity of water, not that one of ice. We are not talking about ice again. So definitely we'll be having Q1, Q2 that we had here, plus Q2, Q3, and Q4. I don't expect them to give you that long one, but just to know, it's still the same approach, just get it. So basically you are going to add it together. That would mean Q1 plus Q2 plus Q3 plus Q4. Yeah, basically that's how simple it is. So another question we have is that 100 gram of ice at minus 20 turns to, so basically this is almost the same thing as the one we did. So see that they already giving the latent heat of vaporization, latent heat of fusion. That shows that that's the way it works. So I already explained how to do that, so I'm not going to solve it for time, but then let me just show you how it will go. So we'll be having ice at what, minus 20 to water at 0 here, abi that's MC change in theta, abi now that's Q1. You solve for it, from this one to from ice at 0 to water at 0, abi this is latent heat of fusion. From water at 0 to what, to water at 100, that's MC change theta. From water at 100 to where, to the heat occurring here is what, latent heat of vaporization. So we're having Q1 plus Q2 plus Q3 plus Q4. Very, very easy. Just add everything together. That's all. So let's move to the next thing. So the next thing we have here is, what is vapor? So basically vapor is water in gas form. We already talked about that, and we talked about what's it called, latent heat of vaporization. That is the hidden heat. So once you know latent means hidden, everything is clear. So vapor is water in gas form. It's what you get when water evaporates. Yeah, exactly. It's invisible, of course it is. So so basically, when does water become visible? When it gets cool enough. Basically, what does this mean? This means that once it starts getting cold, that means losing energy. It's already becoming liquid form. Abi now, so that's basically how your gas, when your gas gets cold and you see them forming droplets. So the first one we have is dew. So take note of what dew is. I would have loved to share pictures, but I don't really have them here. So basically, so on surface like grass, usually in the morning, yeah, that's what they say, all this morning dew and something like that. So what happens is that yeah, near the surface cools at night, reaches the dew point. Exactly. So the dew point is basically the particular temperature the air has to reach for it to time to form what, tiny water droplets. So basically that's dew. Another one we can have is fog. Yeah, exactly, fog. So basically fog is what we have when the air gets cold and condensing into droplets. So it looks like clouds on ground. So basically, when you have this harmattan and stuff like that, when you can't see, you see, the set is hard to see through and drive. So basically, that's what fog is all about. Then we have cloud. You know what cloud is. So warm air rises, cools as it goes, vapor condenses and form. Uh, uh. So basically, so how to tell the difference? The dew is on the surface. I already told you that, in the morning when it reaches what we call the dew point, so it stays on ground. So fog also stays on ground, thick mist, and then this is just water droplet. This is basically mist, like cloud and stuff like that. So the cloud is just floating out, and does it stay on ground? No, you can't see. You have to go up to see the cloud. So that's all about for this part on um latent heat. And so we've concluded our topic for it now. Thank you.